In the world of mathematics and industry, we are constantly looking for the best possible outcome. Whether we are trying to maximize the profit of a business or minimize the amount of material needed to create a product, we turn to optimization. Today, we will learn how calculus allows us to find these perfect values with mathematical precision. Optimization isn't just an abstract theory, it's a practical tool used by engineers, economists, and designers. By defining a situation as a mathematical function, we can find the exact peak or valley that represents the most efficient solution to a complex problem. Before we dive in, remember that the derivative of a function represents its rate of change, or the slope of the tangent line. When that slope is zero, the function has stopped increasing or decreasing. These points, known as critical points, are the keys to finding our optimal solutions. The first step in any optimization problem is identifying the objective function. This is the mathematical expression for the quantity you want to maximize or minimize. If you are building a fence, your objective function might represent the area you want to enclose. Most real-world problems have limits, which we call constraints. You might want an infinite area, but you only have a set amount of fencing. The constraint equation relates your variables, allowing us to reduce the objective function to a single variable that we can easily differentiate. By solving the constraint for one variable and substituting it into the objective function, we transform a multivariable problem into a single variable calculus problem. Now, the area is expressed solely in terms of the width, x, making it ready for differentiation. It is crucial to define the domain of our function. In our fencing example, the width cannot be negative, nor can it exceed the total length of the fence. Identifying the interval of interest ensures that our mathematical solution makes sense in the physical world. To find the maximum area, we take the derivative of our area function and set it to 0. Solving 50 minus 2x equals 0 foot gives us a critical point at x equals 25. This value represents the specific width that will result in the largest possible enclosed area. Let's try a classic example. We have a 12 by 12 inch sheet of cardboard. We want to cut equal squares of size x from each corner and fold up the sides to create an open box with the maximum possible volume. Our objective is to maximize volume. Based on our diagram, the height is x, and the length and width are both 12 minus 2x. Multiplying these together gives us our volume function. Expanding the expression now will make the differentiation step much easier later on. Next, we find the derivative of the volume function and set it to 0. Factoring the resulting quadratic equation gives us two critical points x equals 2 and x equals 6. We must now determine which of these points, if either, provides the maximum volume. We test our critical points within the domain of 0 to 6. If x is 6, the length of the base becomes 0, resulting in a volume of 0. However, if x is 2, the volume is 128 cubic inches. Therefore, cutting 2-inch squares maximizes our box's capacity. To be absolutely certain, we can use the second derivative test. A negative second derivative at a critical point indicates the graph is concave down, confirming a local maximum. Since our second derivative is negative at x equals 2, we have mathematically proven it is the maximum. Now let's look at a cost minimization problem. Imagine designing a can that must hold exactly 500 cubic centimeters. Different parts of the can cost different amounts. Our goal is to find the radius and height that minimize the total manufacturing cost. We use the volume constraint to solve for h in terms of var. Substituting this into our cost function gives us a single variable equation. Notice how the pi and var terms simplify, leaving us with a clean function ready for calculus. Differentiating the cost function and setting it to 0 allows us to solve for the optimal radius. By isolating r cubed and taking the cube root, we find that a radius of approximately 3.63 centimeters will result in the lowest possible production cost. Sometimes, the derivative never equals 0 within our domain. In these cases, the maximum or minimum must occur at the endpoints of the interval. Always check your boundaries to ensure you aren't overlooking the true optimal value. Remember that critical points occur where the derivative is 0 or where it is undefined. A sharp corner on a graph, like an absolute value function, doesn't have a slope of 0, but it can still represent a minimum or maximum point in an optimization problem. A frequent mistake is trying to differentiate the objective function before it is reduced to a single variable. If you have both speed and h in your equation, you cannot simply take the derivative with respect to b without accounting for how h changes. Don't forget the physical reality of the problem. If your math suggests a width of 100 meters but you only have 50 meters of material, the optimal point is impossible. Always cross-reference your mathematical result with your initial constraints. Just because a derivative is 0 doesn't mean you've found a maximum, it could be a minimum. Always use a sign chart or the second derivative test to confirm that your result actually matches the goal of your problem, maximizing versus minimizing. To summarize, optimization is a step-by-step process. Identify what you want to optimize, use your constraints to simplify the math, find the critical points using derivatives, and always verify that your answer makes sense within the context of the problem. Optimization is one of the most powerful applications of calculus. It moves us from guessing and checking to finding exact, provable solutions. Mastering this technique allows you to solve complex efficiency problems in engineering, science, and business. Try this: you want to fence a rectangular garden against a straight wall, so you only need to fence 3 sides. If you have 40 meters of fencing, what dimensions maximize the area? Using our steps, you'll find the sides perpendicular to the wall should be 10 meters. Generated by Vision Solve AI.